Hello, this is Kerry Schutz with MathWorks, and this is my second video on signal averaging. Um, in this video, the second one, we're going to cover three new methods here: dual mode averaging, the triple exponent moving average, and the whole moving average. And then we're going to look at some applications of that by way of spectral average and synchronous averaging, which are really forms of what I'm calling here vector averaging. In the first video, again, if you haven't seen that already, I'd recommend you go through and see that first. That covered three techniques: running average, the sliding window average, which is really an FIR filtering based or finite impulse response filtering based averaging method, and then the exponential averaging approach, which is a form of IIR, infinite impulse response based averaging technique. And there were two variants of the exponential average, the fixed and dynamic. So again, if we just review real quick, the running average approach was the simplest to implement. It just had an accumulator, another accumulator, and then a divider effectively. Very, very simple to build resources wise. The advantage of this approach is that it's very simple to build and understand. It has very, very good quick startup behavior. The downside is that it's very, very slow to respond to changes that aren't part of the startup. So if you have a change or a level shift in the input signal and you want to respond to that later in the process, it's going to be slow to do that. Nevertheless, it's a good starting point. Next, we covered the what we're calling, again, by many names here, the FIR-based averages or the sliding window averages. And we looked at five effectively equivalent implementation variants of that here in Simulink. I showed an explicit delay line filter, one that uses a more efficient form, at least in Simulink, in terms of blocks, using a delay line block. It's a vectorized approach to a delay line. Then I showed how to build it using a FIR filter, a very, very efficient implementation by way of a CIC filter. That's probably the most efficient way to build it. And then, of course, there's the built-in block to DSP system toolbox called the moving average block with using the sliding window method. And we showed how all five of those implementations gave the equivalent response in Simulink. The advantage of this approach, again, they're very, very simple and commonly implemented. Everyone can understand the sliding window method. You're basically applying equal weights to a certain block of data that you acquire, and that window just keeps sliding along in the data. It suffers, though, if you have a large N, you want very, very good smoothing from slow responsiveness because, well, you've got that lag or that so-called like group delay associated with that FIR filter that you have to wait on, which is equivalent to effectively half of the length of the filter. Then we looked at the exponential averaging technique, which is also a very, very common form of averaging and or filtering. And there were two variants of it. There was the fixed coefficient approach, where effectively you're starting with the steady state coefficients for the feed forward and feedback coefficient. That mean 1 over n and 1 minus 1 over n. These coefficients must always sum to 1. And then we looked at the dynamic version thereof, where the coefficients are always going to sum to 1 still. However, they aren't going to start at their steady state values. Initially, the feed forward coefficient would start at 1 and the feedback would start at effectively like 0. And then they would start approaching their steady state values. And so the advantage of the dynamic exponential averager is that it has much better, you get the nice quick startup behavior like associated with the running average, but you don't suffer that effect as N increases or time grows on, that you don't suffer from that slow responsiveness in the long run because compared to the running average. And then there's also a built-in block in part of DSP system toolbox called, again, the same block moving average, but it's got an exponential averaging mode associated with it. Okay, so today we're going to start new focusing on the dual mode averager, which is a combination of a running averager and an exponential averager, and it kind of seamlessly blends the two together so you kind of get the best of both worlds. Let's take a look at how this works. We've got something in here called mode control subsystem, and that is what controls the switching between the two modes, running average mode to exponential averaging mode. And the way that works is we've got an accumulator or counter in mode control, which counts up to n. And while it's counting up to n, it's going to be in running average mode. So again, for the first n samples, it's in running averaging mode. So as long as this number here is less than n, the output of this comparator will be 1, which means it's passing 0 through this switch to the output on to some junction 1. And that means the input to this minus import of this adder is also 0. Now, if that's a 0 there, this is serving as a perfect accumulator of the input, and the multiplier at the output is just multiplying by 1 over n, as multifact actually in this case is just the inverse of the sum. In this case, it's outputting 1 over n. And so that's the definition of a running average. You sum and then you divide by n. Again, that's in the running average mode. And again, by dividing by n here, I mean the lowercase n, 1 over n. That's in the running average mode. The 1 over capital N here denotes the exponential averaging mode. In that case, what we're going to do is we're going to turn this first accumulator into a 1 minus 1 over n weighting factor. And the way we do that is, first of all, we get the perfect 1 factor here in this accumulator here, and then we're going to get the 1 over n factor in the feedback term. That's what we're going to feed back, and we're going to subtract that. So effectively, we've got the 1 minus 1 over n when you combine the two together. And then, of course, with the feed forward term, we've still got our 1 over capital N there. And that's going to serve as our exponential averager. Again, we're using it only in the steady state definition of the exponential average, not the converging sense. For the converging mode, we're using running averaging. For the steady state mode, we're using the exponential averaging mode. So let's take a look and see how that works. Let's just run that in the actual system, in the actual model. Let's see, let's go to that. That's exponential averaging. I want the dual mode average, which is here. Again, first running, then exponential. You can see the same system I just showed you in the slides there earlier. We've got some words about how it works. Let's go ahead and hit the play button. We're going to run this for 2,000 samples, where each sample is 1 second. And we see how it works. We've got the yellow noisy input signal, and then we have the average version of it in blue. So we can see the startup behavior in blue of the blue signal. On the left, it has a little overshoot and undershoot and then settles nicely. And then we have this sudden level shift at 500 samples, and then we see how it adapts thereafter. All right, so that is our dual mode averager. Okay, I wanted to say that before I moved on, I did have a typo in the title of my dual mode averager, but initially it said dual model averager. It should have said dual mode, and so I wanted to correct that before moving on. I'll save that and close that model. Okay, the next model I'm going to open up, it's going to introduce 2 new averaging methods that come from the finance industry. One of them is called the TIMA, or triple exponent moving average. Other is HMA, or Hull moving average. So I can just peek under the hood of the triple exponent moving average. It's just called triples because we've got a cascade of 3 exponential averages, and these are weighted and summed in some way, as shown here. And there is a Wikipedia reference on how this works. So I won't be going into the derivation of it. I'm just showing you how it works. Again, each averager is set up as an exponential averager. Okay, and then the other is the Hull moving average. It consists of 3 different moving average blocks, but they are not exponential averaging in this case. They are set up as classic FIR filters, but they are not equally weighted FIR filters. They are weighted. The weights vary from essentially from one lag to the next. So, and linearly so. So, for example, the tap with the least delay has the largest weighting. So, if it doesn't have any delay, it has the highest weight. And of course, the most delayed sample has the least weight applied to it. And again, it's a linear drop off from the greatest to the least. So in this one, and the lengths of these filters all vary. So the top one, called WMA1 here, has a length of half of n. So in this case, if n is 100, this length would be a 50 element filter, or tap filter, as indicated here. The one below, WMA2, has the full length of 100. Okay, again, same weighting concept applies. And then the last one, which is a weighted sum of the first two, has a length, the shortest length, typically would be square root. So that, in this case, that would just be, if n is 100, that would be 10. Again, same weighting concept applies from greatest to least. All right, and there's a link there as far as how this particular averaging method came to be for the finance world. Let's go ahead and run this model and see how it performs. Again, we'll be comparing against the methods we already introduced, the exponential, the sliding window, and the dual mode averager. Okay, and there's three kind of periods we want to look at. Again, it's the input, noisy input on top, where we start at a noisy 1 level, then we jump to a noisy 2 level, 500 samples into the process. There's sort of three you could call it interesting areas to look at in the response or in the output, that being the startup behavior, the steady state behaviors, and the kind of midstream level shift behaviors here at the 500 sample point. So let's go ahead and look at the startup behavior first. The purple and the green are the new methods we're introducing, that being TEMA and HEMA, if you want to just use short names. You can see the triple exponent starts up really fast. It has a lot of undershoot and overshoot, but then it settles down. The HEMA, or whole moving average, starts up much slower, somewhere between the exponential approach and the sliding window, which is the slowest here. And then if we look at what happens at the level shift point, 500 samples in, you see that it's kind of a flip-flop scenario where now the TEMA doesn't respond the fastest. Actually, the whole moving average does. And then TEMA, and then comes the sliding window next, and followed by the slowest here being the dual mode average and the exponential average. And if you recall, the dual mode averager actually is exponential averaging the steady state, so we would expect them to align quite well. And then for steady state, if we look, the whole moving average is very noisy in steady state, and the TEMA is not as noisy, but it's still pretty noisy. And of course, the dual mode average or exponential average is probably the quietest. So if I take off, maybe I'll just take off TEMA, I'll take off sliding window, and we can see a significant difference in how exponential and dual, which again, these overlap, the red and the yellow overlay quite nicely, versus the whole moving average, which is quite significantly noisier in steady state. All right, so that's all I'm going to show there on all these different averaging methods. And again, the main thing to keep in mind is there's really only fundamentally here two averaging methods, that being exponential and sliding window. And then what we've done is we've combined them in some way to create these other variants that I'm showing here: dual mode, triple exponent, and whole moving average. Okay, so the next thing I want to get into, I'm going to first close this model down, is I want to get into some applications of averaging that are different from what we've already covered. Thus far, what we've done is, in fact, I'll just bring back my PowerPoint slides, is we've taken a noisy time domain signal, and we've streamed, which is a streaming signal, and we've applied this into some type of filter, FIR filter, IR filter, and then we've come up with a filtered and less noisy version of that time domain signal. It's smoothed it. But we have not decimated the data in any way. It's not like we've taken all of this data and then condensed it down to a few samples. We have not bandwidth reduced in that sense, or we haven't data reduced. We have bandwidth reduced, but we haven't reduced the amount of data we're dealing with. We've just smoothed it out. Okay, as you can visually gather from plots like this for the exponential averager. Now, what I want to get into next is a little different. I want to get into frequency domain averaging, or what's also called spectral averaging. And really what this is, it's really a multi-dimensional, it's still time series averaging of a frequency domain quantity. So, but at its core, it's really still averaging across time. So what we're going to be doing is we're going to take multiple FFTs, you could say, or multiple power spectras. You'll take one at 1 second. You'll capture a bunch of time domain data, let's say 1 millisecond's worth of data. You'll compute the spectrum of that. Another 1 millisecond comes along. The next 1 millisecond, you'll compute the power spectra of it, and so on and so forth. Just keep doing that. And what you're going to do is you're going to take the energy at each FFT bin or each power spectrum bin, each frequency, and you're going to average across time. And of course, each value is a frequency domain quantity, but those frequency domain quantities are spaced in time by 1 millisecond. In this case, it could be whatever, based on whatever your sample rate and FFT size is. And so we're going to go across each frequency bin, and then we're going to go across time for each frequency bin, and then we're going to come up with an average value. And so that will be, in this case, a less noisy, if you will, it's kind of using the word noise here differently, a smooth or an improved estimate of the power spectrum. The key thing to keep in mind is that spectral averaging does not reduce the noise in the original time domain signal. What it's really doing is better estimating the noise in the signal. Okay, so the way I've used averaging thus far was actually to reduce the noise in the time domain signal, but we're not doing that here. We are just using spectral averaging to better estimate the noise, a key important difference. So let's go back to the model. Let's go to show this. In this case, I have a sine wave, in this case, a fixed frequency. I think I had it set to 50 kilohertz. The sample rate is 1 megahertz. I've got an FFT size of 1K, 1,000 FFT points, and I'm adding some noise to it. Okay. And so again, we could look at what that looks like in time. But what I want to focus on up here is the spectrum. So I've got a spectrum estimator block, and then feeding that into a visualization block. I'm also directly computing the power spectrum here on this block without going through an intermediate spectrum estimator. The only difference in these two cases is in the top case, the spectrum analyzer looking block is only used for display purposes. It's not computing anything. And in this one, the spectrum estimator itself is baked inside of the spectrum analyzer block. And the way you distinguish is you just change the mode of operation on the blocks. You can change it from a frequency domain mode to a time domain mode. Okay, so I'm going to run this model. We'll look at the topmost visualization block, SA from SE, spectrum analyzer from spectrum estimator. And you can see that in this case, it is taking averages. Actually, I should say it is. It's doing, if we look at it, it's doing 100 averages. And this is the resulting spectrum. Okay, the power, the baseline, the noise floor is down about minus 27 dBW. Now, if we didn't use averaging at all, if we just said averaging was 1 average, run it for the same amount of time, run it again, we're going to get a very different looking noise floor. So I'll just kind of put my mouse where the noise floor was, and you can see it might be centered around minus 27, but certainly it has a larger variation about it. Okay, so you can see the benefit right there. You get a better estimate of the noise floor using spectral averaging. Okay, this block effectively does the same thing, except in this case, all of the spectrum estimator features were built in directly to the block. So when you go underneath a block, you can always set the input domain to time or frequency. Here it's time. On the block up here, the difference is if I click on this, the input domain is frequency. So again, this block does not do actual FFTs. It's just displaying the results of the previous block. Now, we can apply this same technique, this vector averaging technique, because again, we're averaging across a set of FFT bins, and we're doing that, across time. We can also apply this to what we would call synchronous time domain averaging. And in this case, we are going to reduce the noise in the time domain signal. So if I go back to my PowerPoint slides a second, go to the next slide. Here we've got synchronous averaging, where we're acquiring, instead of successive power spectrums, we're acquiring successive frames of a signal in time. We've got 0 to, it could be 100 seconds or 100 samples. In this case, it's just in units of samples. We got the next 100 samples, the next 100 samples. And what we're here is we're assuming the signal is synchronous with respect to our analysis window, our display window. And if it is, we can average across samples from one frame to the next. And if there's noise, that noise should average out, and you should be left with the signal of interest, that periodic signal of interest. And that's what we're showing here. We end up closely recovering our sine wave by just averaging across time of these noisy time domain frames of the same underlying core signal. And I've got a model here. This same model that I had up is showing that concept. I've got a filter block. It's set up as an FIR filter. I am using, I said that wrong. It's actually set up as an IR filter, exponential averaging. You could use FIR filtering, but I'm using exponential averaging here. And I'm using kind of that same concept before, where I pick some value n, which is going to set my forgetting factor, which is 1 over n average minus 1. We set up, that filter as such, and then when we run it, what we're going to see is, that this filter, of course, has a transient response. It has a time constant to get to steady state, but as you get closer to steady state, what you're going to find is the signal is less noisy and more closely resembles a sine wave, as shown the difference between the input signal on top and the the synchronous average signal on bottom. So in the bottom case here, we are using the averaging method as a noise remover, whereas on top, we are using averaging as a noise estimator. All right, so that's all I really wanted to cover on these two sessions videos on signal averaging. I hope you found it helpful, and thank you for tuning in.